Greetings, we are at the desk and we are trying to show you the implementation phase of lab number 5. We have an inductor and the inductor is supposed to be set at 0.1 Henry. So that's inductance 1 and 0.1, everything else 0, these two red. I'm going to use it. When I go into the capacitance, I'm going to put this to 0. This is capacitance, microfarad. I put that to 1. Everything else is 0. This is really nothing because this is 10 minus 4, extremely small, so I'm not worried about this. This is going to be an indication that I'm going to get the 0.01 microfarad from this one. Now, part of the lab is on the working on the resistor, which is 1 kilo ohm, and either of these two, second column, third resistor, I'm going to use that. I'm going to turn on the oscilloscope. There is a power on button at the top left-hand side of the oscilloscope. I'm going to let that to warm up a bit. I'm going to turn on the function generator. By default, you can see this is set to 1 kilo and this is set to a triangle waveform. But I want a sine cosine waveform, so I'm going to make sure this is going to be sine cosine waveform. On the first row, you're going to see the scalar value that is going to have an impact on the values I'm going to see. For example, if I say 1, obviously this is going to be 3 hertz now. If I say 100, this is going to be 321 hertz. If I say 1K, 3.1, 10K, 32K, and so on. So let's let it be as it is. Now, one of the things I did on the oscilloscope, because the last time it wasn't as much visible, I actually pushed the display. And if you push the display, you have the display style as inverted and non-inverted. This one was not as much visible to some, so I decided to use the inverted value display style. If I do inverted, the background is going to be black, and hopefully you would be able to see the signal clearly this time. Now take a look at what we were supposed to do. From the inductor, I'm going to use the red because obviously red is more visible in the clip. So I'm going to go from inductor, there is no polarity at this time, to my capacitor. I'm going to go from capacitor to my resistor, and I'm going to begin supplying this with incoming voltage source. So I know that this is set to sine cosine. One end of the resistor is supposed to be ground. This is now my ground. Remember, all the grounds, the ground of the function generator, the ground of the oscilloscope, everything has to go into the same node, and this is going to be supplied to one end of the inductor. So take a look. The source is coming in. I'm going to go into the inductor. I'm going to go into the capacitor, going into the resistor, and coming back to the ground of the function generator. I'm set in terms of the function generator. So let me see if I can actually put them inside so that I have a better view. You guys have a better view of my process. So let's begin with channel number 1. Once again, make sure all the black line or all the ground lines are actually connected to the same. And the red one for channel 1 is supposed to actually capture the incoming signal. Don't worry about that. This is actually channel 1. I'm going to open it. And you can see a very good signal now, I hope. Now, it says 6 volt peak to peak. I'm going to actually divide it in two. So I have 3 volts on top and 3 volts at the bottom. So this is 1.3 units, 1.3 units times 2 volts per unit. So I've got about 6 times 2, 12 volts peak to peak. I need to go into the amplitude, and I'm going to reduce this slowly, hopefully, and I'm going to expand channel 1 because I want to have a nice reading. That's now 1 volt per unit, which means every unit that you have on the vertical axis is going to be 1 volt. I need 6 volts peak to peak, which means 3 volts on top, 3 volts at the bottom, and I want to kind of make sure that the 3 volts are kind of symmetric. So I'm going to take it down and almost there. I'm going to claim now that I have 3 volts on top, 3 volts at the bottom, and also I'm going to say that it is symmetric. I need the symmetricity because I need to measure the tau correctly, the theta correctly, the phase shift correctly. So I need to do that. Now, That's channel number 1. I made everything working at this time. I go into channel number 2. Channel number 2 has a ground. Now don't worry about the color. It's going to be ground. All the grounds are connected in the same node. And the other side, which is capturing the signal itself, is going to be on the other side of the signal resistor. You can see there is a small signal coming in. You can obviously magnify it. This is 5 volts per unit. I want to magnify it so that you can have a better reading. What I need to make sure, though, is to make sure that the channel 2 is also symmetric. You need to make sure that both of them now, unlike what you did in lab number 4 or even previous labs, you weren't as much sensitive to the reference of this. I need to, both signals to have the same reference. So take a look at this. I have my original signal and I have my measured signal. This is 500 millivolts per unit. So obviously this is going to be small. I need to divide that 500 millivolts to 1 kilo ohm in order to capture the IL, IC, IR, or I total, because everything is going to be the same. Now V divided by I. What I mean by amplitude is that measure this amplitude, which is 6 volts peak to peak, or you can even measure it as long as you are in good shape symmetric. You can say 3 divided by almost 2. So the gain, obviously divided by 1000. So this is going to be 3 volts divided by 2 volts divided by 1000, 1 kilo. So you've got voltage, you've got, you capture the current, obviously divided by 1K, remember that, and you're going to read me the input impedance. Where is my phase shift? Now this is the incoming signal, and you can see that this is going to be the outgoing signal. There is a bit of a delay between the IC or IL versus the VIN, IN and VIN. Again, once again, that 1000 factor, keep that in mind. So I'm going to say, let's count this. You are going to see, in my case, 1, 2, almost 3 little units. 3 little units. You have 100 microsecond. So every 5 units is 100 microseconds, and you have 3 of that. 3 divided by 5 times 100 microsecond. That's going to be your delta T. You have your delta T. That's what this is. You also have your capital T. You need to measure the capital T from this 0 to this 0. So from this 0 to this 0, you need to count this. Count everything that you have, and you also need to multiply by 100. If you don't account for 100 microsecond for both signals, you're fine. You just need to count the units. So count the units for the period, count the units for the shift. This shift is supposed to be the same as this shift anyway. Delta T divided by capital T is equal to the theta I'm looking for divided by how much is the capital T for. Let me actually try to explain that on a piece of a paper for you. Now here is my signal, and here is a secondary signal, and as we discussed, this is going to be delta T. Let me tell you, that's one of my signals. This is another one, so it doesn't matter whether back or forward. If it is back, it's going to be minus. If it is forward, it's going to be plus. So this is going to be delta T. You measure that exactly. You have the period of the signal, and the period of the signal is not supposed to change. And what happens is that this is going to be delta T divided by T as equal to theta divided by 2 pi. Because the capital T represents one complete cycle, the capital T represents one complete cycle, right? It's going to be 2 pi. For capital T, I have 2 pi. For delta T, how much do I have? That's going to be your phase shift. You need to measure the phase shift for different frequencies. Capital T, 2 pi, delta T, how much? We know that from high school. So if you take a look at this, I have an originating voltage, Vin, and I have a concluding IN, obviously the factor 1000, once again keep that in mind. Now let's go back to very small value, say 100. I'm going to remember that in this experiment you need to make sure your originating signal is still 6 volts peak to peak. Sometimes, because that R we have in the design, this R that we have in the design might be extremely small. If this R is small, then obviously that 6 volts may not be correct because of the loading effect this is going to have on the function generator. So if this is a small, then you need to watch for that. But in this lab, we made this intentionally 1K so that this issue is resolved for all of you. So you have a 6 volts peak-to-peak. You always keep that in mind. Channel 2 is in your possession. You can actually magnify it. Make sure it is symmetric, right? It's extremely simple, small now. 50 millivolts per unit, and obviously almost symmetric. If it's not symmetric, you have to play with that to make it symmetric. And then this is your delta T. And then obviously the period of the signal, you can get that. The period of the signal sometimes is also written down on this side of the screen scope. It captures that actually. So you take a look at this and see what happens when I increase the frequency. When I go into 1K, say let's go for small values, and take a look at both signals. You can see this is rising up. This is remaining the same. Don't let it trick you into believing otherwise. The originating signal, because of that 1K, is not changing peak to peak, but the I is actually rising up. You can see that. So this ratio is actually coming down. Now, as I raise this frequency, what happens? Let's go more and more and more. I want to open it so that you can see it better now. Always play with this to get the better reading. So I'm going to raise it to 1K. Hold on, let me actually show you what is happening. Okay, take a look at this now. Don't worry about this exceeding because the unit, the millivolt, the volt per unit is actually different. So it's going to come in. You can see that after some frequencies are achieved, it's actually coming down again. So it is open line, minimum, and then it goes into a maximum. In terms of the theta also, you're going to measure that and you're going to see it's going to go from minus 90 degrees to plus 90 degrees. So which means the signal originally, let's go back to 100 Hertz, the signal originally was lagging. Let me show it to you. So you can see the signal is behind. When I go to 1K, again, this is part of your observation, and I want you to achieve that. And when I go even more, you can see that it is approaching. It's going to go into in phase, the same phase. That's why it is much the same as an Ohm law, much the same as V and I are in the same phase. I'm going to go in. You can see they are going to capture. Let me actually increase my frequency once again. Open it, please. I just want to show you what is happening. Now, then I'm going to go, and you can see that the signal is actually now happening after this. This is not symmetric. You have to make sure it is symmetric, though, in order to calculate the delta T, and then you're going to be fine. So the signal begins lagging, then the signal is going to be leading in terms of what you see on the screen. The intention in lab is to see that the input impedance now is varying, be it frequency, and we are going to measure the amplitude, we are going to measure the theta, and we are going to start discussing what is happening actually in the design. You could have RLC in series, you could have RLC in parallel, you could have many other combination of RLC, but you need to know the feeling that the system is now frequency dependent. Thank you very much.